Hi, this video is to answer a question regarding how to complete the sign table for the function f of x equals x to the fourth minus 4x cubed. If you notice in the sign table, we are talking about the first derivative and the second derivative. The first derivative, of course, we know we will determine critical numbers, and from there we will test to see if we have an increasing or decreasing function f. With the second derivative, we are able to find inflection points, hopefully, where we are changing concavity. And so what I've done here is I have attached, not so beautiful handwriting, but I have attached a discussion of how to approach this problem. So first of all, we've got our function, it's a polynomial, and I start realizing when I take the first derivative that the first derivative of this function is going to be continuous. We're working with a polynomial, and this derivative is going to exist everywhere. The polynomial exists everywhere. So the critical numbers are only coming from when I set the first derivative equal to 0. So when you take the first derivative, you have 4x squared times x minus 3. And setting this equal to 0, that first derivative, you would get that x must either be 0 or x would have to be positive 3. Your next step should then be to test on a number line. So we break this up into intervals. We put on the number line our critical numbers. So we have x equals 0 and x equals 3. And we test x values in between each of these intervals. Something to the left of 0 is going to be x equals negative 1. And what you're doing is you're testing the first derivative to see if it's positive or negative. What we know is that if the first derivative is positive, then our original function f is increasing. And hopefully that makes sense, because when you think about what an increasing function looks like, and you draw the tangent line on an increasing function, you would see that the slope is positive on that tangent line. And of course our tangent line is going to be the same thing as our derivative at that point. So anyhow, our first derivative, if it is positive, will indicate that our function f is increasing. If our first derivative is negative, it will indicate that our function f is decreasing. So what we're plugging into then is the first derivative, and so we take a value like x equals negative 1, and I always use this factored form of my first derivative. So if I plug in negative 1 on the outside, I go negative 1 squared times 4 is going to be positive 4. So it's a positive result on the outside, right? Negative 1 squared is positive. So on the outside I have a positive. If I plug in a negative 4 into the set of parentheses x minus 3, well, why did I say negative 4? If I plug in negative 1 into x minus 3, I'm going to have negative 1 minus 3. Well, that's a negative 4. I guess I was already doing the arithmetic. So I'm going to have a negative from that set of parentheses. So I have a positive on the outside times a negative, which gives you an overall negative. That means that the first derivative is negative for any x that is to the left of 0. So if I pick negative 100, it would also have the same result. Okay, well, if I got my first derivative was negative, then that means that my function f is decreasing. The symbol that we're going to use on the table on my math lab is going to be this, caret, and so it's like a down arrow that's saying we're decreasing. Likewise, you're going to do the same thing as we test between the interval 0 and 3. So I picked x to be 2. You could have picked x to be 1. You could pick 1.5. You could pick anything between 0 and 3, because we're just testing to see what's happening to our first derivative. So my first derivative, if I plug into our first derivative function here, I go 4 times 2 squared. Well, that's going to give me a positive result. So right here's my positive result. If I plug in 2 into that set of parentheses, I'm going to have 2 minus 3. That's a negative 1. I don't care about the actual numeric value, but I know that I will have a positive times a negative, which results in an overall negative. That means my first derivative would be negative for any x value I choose between 0 and 3. Okay, so again, that means that my function then is decreasing. So we have this this indicator here. Okay, Now let's look over here on our next interval. So on the other side of this critical number 3, I can pick anything. I chose x to be 4. If I plug in 4 times 4 squared is a positive number. So I have that plus sign written. I'll have a positive. And then on the inside of this set of parentheses, 4 minus 3 is also positive. So I'll have a positive times a positive. Positive times a positive gives you an overall positive, which means my function then is increasing. So again, think about what a derivative is. It's a rate of change. It's the slope of the tangent line at that point. And so if I think about drawing a tangent line to a curve, if it's positive, which is what it says here, that means my original function is increasing. Okay, so we've gotten through part of this. Let me pull up the other screen here. Okay, we've gotten through part of this of how we're going to have the increasing and decreasing, but there's a whole lot more to this, right? Okay, well that's where I have to start working with the second derivative. Okay, so I'm looking at now the second derivative. I took the derivative up here. The derivative of the first derivative is called the second derivative. And I have the second derivative is 12x squared minus 24x. Well, I went ahead and factored it because that's pretty easy for me to plug in my test points. So if you factor it, we've got 12x times the quantity x minus 2. So I solve this when it's set equal to 0, right? Our inflection points are going to occur where the second derivative is equal to 0 or where it doesn't exist. However, this is a polynomial, so it's going to be continuous. I don't have to worry about where it doesn't exist. And so I find out the inflection points coming from 12x equals 0 would be x, the x coordinate would be x equals 0. And I have that from the x minus 2, if I set this equal to 0, that if x were 2, this would make my second derivative 0. So on a number line, you plot these x values for the inflection points. All right, and we're going to see if they're inflection points and if indeed we change concavity. So we plot on our number line x equals 0 and x equals 2, and we test an x value between each of these intervals. So something that's to the left of x equals 0 is x equals -1. If I plug in -1 into my second derivative, I like the factored form, I go 12 times -1 is a -12, so I put down my negative here. Then I go, if I plug in a -1 into the set of parentheses, I go -1 minus 2 is still a negative, so I'd have a negative times a negative, which gives you an overall positive second derivative. Well, we've learned that if your second derivative is positive, that means that your function f is concave up. So I've got it concave up from -infinity to 0. And now I'm going to look between 0 and 2. So a number between 0 and 2, I could select x to be 1. I'm going to test what's going on with my second derivative. So 12 times 1 is a positive 12. So I've got a plus sign down here. I take 1 minus 2, that's a negative, so I've got a positive times a negative, which gives you an overall negative for your second derivative. Well, if your second derivative is negative, that means that your function f, your original function, is concave down. Okay, then you move to the next interval, which is to the right of x equals 2, so I chose 3. 12 times 3 is a positive number. 3 minus 2 is a positive number, so positive times positive gives you an overall positive. And we would have that we are concave up. Okay, so how does this all work? Well, let me see if I can pull up this image here. So what intervals am I talking about? Well, I need to worry about my second derivative intervals and also my first derivative intervals that we found from inflection points and critical points, respectively. And so from -infinity to 0, I'm going to have that my second derivative is positive, as I show, and I'm going to go back and I'm going to look at what's going on based upon my intervals and my number line that I constructed with my first interval test. You need to be very careful about not putting in spaces and things like that so that my math lab recognizes what you're intending to say. So the IP, for example, is inflection points. So we have x equals 0 and x equals 2. We've also gotten here that x equals 3 was a critical number. We did not have an indicator for saying critical number, rather we would say that's where the first derivative was equal to 0. So, just kind of, hopefully this example will help you with your conclusions. So if you have any questions, please let me know.